Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 11, 2025, which was about 5 days ago. The striking claim is that locality in image diffusion models comes from the training data's pixel correlations, not from convolutional network inductive biases. The paper is titled, Locality in Image Diffusion Models Emerges from Data Statistics, and the implications for model training are quite significant. In short, the authors show that a simple optimal linear denoiser mirrors deep models, locality, and that data-driven sensitivity masks yield better analytical denoisers than prior handcrafted alternatives. Also, the authors shared a GitHub repo. It is the official implementation, but right now it mainly has a README and a note that code is coming soon. You will find the paper details, author info, a citation block, and plans for releasing the analytical denoiser and reproduction scripts. So, Figure 1 illustrates why trained denoisers can generalize while the optimal denoiser cannot. The left panel marks sampling voids, which are low data regions in noise level and image space where training provides no examples. The central montage shows pass-through behavior, meaning the network preserves coarse structure at low noise, so the output resembles the input. The right plot reports error versus noise, showing large gaps at low noise because the optimal denoiser snaps to nearest neighbors. So, Figure 3 shows that sensitivity depends on where a pixel sits in a face, which means the denoiser reacts differently across locations because the dataset lacks translation symmetry. Sensitivity field means the map of input pixels that most influence one chosen output pixel. The top row targets a pixel near the left eye, while the bottom row targets the image center. Left to right, lower noise sharpens and narrows the hotspots, confirming location-dependent, non-equivariant behavior. So, Figure 2 shows that denoiser sensitivity on CIFAR10 looks the same across very different backbones and matches a simple Wiener filter, which means a data-driven projection that keeps high signal components. The heat maps compare a diffusion transformer, a U-net, and a high SNR projection across timesteps. The bright central blobs shrink as noise drops, which signals increasing locality because nearby pixels dominate. This alignment implies the dataset's pixel correlations set the receptive pattern, while architecture mainly carries it. Alright, Table 1 reports how closely each analytical denoiser matches a trained model, which matters because a better match means the analytical rule captures the learned locality. The table shows that our data-driven mask model scores best across datasets, while a simple Wiener filter usually comes second. R-squared measures, explained variance, and mean-squared error tracks average prediction error. Another DDPM, with a different seed, sets an upper bound since it shares training but not initialization. Wrapping up, 2 takeaways stand out. Locality mirrors data pixel correlations, not just convolutional inductive bias, and simple Wiener-style projections already explain trained denoisers, enabling better analytical surrogates without hand-tuned receptive fields. The broader implication is practical control. Shaping dataset covariance could steer generative behavior. That is it for the AI Research Roundup. I am Alex. Thanks for listening.